When a data mine run finishes, we get taken straight to this definitions page. We can also access it at any time by selecting definitions from this navigation menu. The data mine run that we ran in the last video created this set of segment definitions, which contains 1, 2, 3, 4, 5, 6, 7, 8, 9 different segments. Let's sort them from highest ratio to lowest. So this column here just provides a unique key for each segment. These columns here define the segments. So for example, this segment here is people where the largest amount lost range fell into either the $501 to $1,000 categories, the $100 to $500 categories, or the $1,000 plus categories, and where the effects of legal gambling was either 5, 1, or 4, or less than 0, and so on. By contrast, this segment here is defined as being where the largest amount lost took the same values as the previous segment, but where effects of legal gambling values were either 3 or 2. This segment here is where race groups took the values either black or African American, and where largest amount lost range was in the never lost any money, missing, or under $100 categories, etc. Now, a respondent is allocated to a segment by meeting all of the criteria across here. Blank means that the predictor isn't important in defining that particular segment, but it might be important in defining another segment. Race grouped being one example where it didn't come into effect in the first two segments, but it does come into effect down here. The segment definitions are mutually exclusive and exhaustive. This means that across the 9 segments, there are no gaps or overlaps. Every respondent falls into one and only one of these 9 segments. Now this column here shows the sum of the response variable in each segment for the 70% of cases that were in the training set. So this is effectively the numerator in the ratio that the data mine algorithm is segmenting on. Even if we're not actually interested in modeling a ratio as the response variable, for the purpose of the algorithm, it still treats it as if it is a ratio, though with the denominator always 1, i.e. the number on the bottom of the ratio being always 1. OBS here is effectively the denominator in the ratio, so it's effectively the weight, because OBS here is effectively the denominator in the ratio. Because both the numerator and the denominator are weighted by the weight variable that we selected, which in our case was sample weight, the sum of OBS train will, across all of the segments, will effectively sum to the sum of sample weight. And this is the ratio itself. This ratio is this number here, 257, divided by this number here, 202. And same calculation going down for each segment. For respondents in this segment, the average gambling score is 1.28, which is well above the overall average of 0.229 that we mentioned earlier. And similarly, once we get down here, it's actually 0 for this segment. These columns on the right here show effectively the numerator, denominator, and ratio, or response, OBS, and ratio for the validation data, as opposed to the training data. Model validation will become more important in the next video. So the main conclusion we can draw from this is that the very high gambling scores, i.e. those where the average is actually 1.28 as opposed to all the others where the average is below 1, are those where they had a largest amount lost of greater than $100, i.e. they fall into the 100 to 500 or 500 to 1000 or 1001 plus. So effectively this whole segment is defined as being 100 plus. And where the effect of legal gambling is at the extremes, either 1, 5, 4, or missing. The next worst category down is where the largest amount lost is also in that 100 plus category, but where their attitude towards the effects of legal gambling is more moderate. So it's in the 2 or 3 range. And if you recall from the GLM modeling video, we showed that there was a bowl-like or a parabolic shape to effects of legal gambling, where people with moderate views on the effects of legal gambling didn't quite have as high a gambling addiction score as those with more extreme views, i.e. with attitudes of 1 or 4 or 5. So you can see how at the click of a button we've been able to quickly identify what variables are the most important, largest amount lost, effects of legal gambling, and what pockets of respondents had very high gambling scores. The other extreme, we can look at those people that had very low gambling addiction scores. It looks like those who had relatively low scores were typically in their race group was in the white or other category. They had only lost small amounts of money, being under $100 or never lost any money. And you might be able to infer something from here around the fact that they tended to live in the south, northeast, or midwest. Now, these conclusions were drawn from segments of the size of about 200 people on a weighted basis. 202, 262, and so on. Do you think it's reasonable to draw conclusions on segments that only have about 200 cases in them? Is 200 enough? Is 200 too much? Could we have gone more granular and picked out more segments each with 50 people in them and drawn more insight, or do we need to group up the segments because 200 people just isn't enough? We have some metrics to help us find the optimal minimum segment size. Now, we measure how good this segmentation was by looking at a trade-off between what we call lift and correlation. Lift is the difference of the ratio between the top and bottom segments. In this case, it's 1.28 minus 0, which is simply 1.28, as shown up here. Now, we can improve the lift by reducing the minimum segment size and hence increasing the number of segments. If we reduce the minimum segment size from 200 to say 100, the number of segments might jump from 9 to 18 or higher. With say 60 segments instead of 9, the top ratio here is likely to be quite high and the bottom ratio is likely to be quite low, or remain at 0. The problem with that arrangement is that with so many segments on so little data within each one, the ratios that have been calculated for each segment probably won't generalize well. We wouldn't have a good model in that case. To test how well the model generalizes, we need to compare the ratio on the training data against the validation data ratio for each segment. Recall that the validation data wasn't used in coming up with the segment definitions at all. Preddle finds the segment definitions using the training data and then runs the validation data, which was held out on the side, through these segment definitions to allocate each case in the validation set as we see here. If there is higher correlation between the ratios from the training data and the ratios on the validation data, then the segment definitions probably generalize well to further data that we haven't even included in this analysis at all, i.e. the entire population, as opposed to just the data that we collect. So let's just eyeball the average gambling scores between training and validation data to get a feel for what's happening. For the top ranked segment, the average score on the training data was 1.28. While on the validation data it's 1.06. That's not bad. On the next segment down, it's 0.52 compared to 0.513. That's pretty good. And the rest of the segments line up pretty close. You can see here 0.0821 versus 0.0452. This one's not great. 0.0705 versus 0.21. As we get down here, we can see 0 versus 0, and 0 versus 0.0391. So generally, where the training ratio is high, the validation ratio is also high, and where the training ratio is low, the validation ratio is also low, which is good. In fact, the correlation on this data mine run is 0.99. The maximum correlation possible is 1.00, so this is pretty close to the highest possible. Now, a correlation between about 0.9 and 0.95 is pretty good. Any higher than this, and you could have gotten more lift by allowing the model to find more segments, i.e. more than the 9 that we have here. Any lower than 0.9 and the segmentation won't generalize well, so you would need to generate fewer segments. Subject to keeping the correlation in this 0.9 to 0.95 sweet spot, usually we would want to push the segmentation as hard as we can, and by that I mean have as many segments as possible to push the lift as high as possible.